On this episode of MRI Physics Explained, we continue our journey exploring diffusion-weighted imaging with a topic so difficult that this guy needed help with the math on it. No, this isn't a lecture on general relativity, but an equally cool and difficult subject: diffusion tensor imaging. What is a diffusion tensor, and how do we use it to map white matter tracks in the brain? All of this and more coming up on the latest episode of MRI Physics Explained. Welcome back, my friends. Dr. TE here. Let's recap where we are in this diffusion-weighted imaging lecture series. In the first lecture, we focused on the physics of diffusion-weighted imaging, where we designed a pulse sequence to detect water movement in the brain, and along the way explained exactly what these terms DWI trace, ADC, and B value mean. These topics are so important that we then took an unexpected turn and gave a lecture on how to interpret diffusion-weighted images and the many pathologies that cause restricted diffusion. Links to these lectures are above, and I highly recommend you reviewing them before tackling this lecture because, oh boy, are things going to get complicated. Going back to this first lecture, we got lazy. Or maybe that's a little too harsh. Let's say we were less ambitious than we could have been. Let me explain. We developed this diffusion-weighted pulse sequence that we ran 3 times, each time with a unique diffusion sensitization gradient shown here. Once with the gradient across the x-axis, again but with a gradient across the y-axis, and one more time with the gradient across the z-axis. In doing so, we were able to generate these 3 corresponding images, which look slightly different from each other, and we didn't quite know what to do with them, so we said, let's just average them together. This produced the following image, which we call our DWI trace image. Now, mathematically speaking, this looks like so. Notice this term on the right. We have 3 different diffusion coefficients, dx, dy, and dz, corresponding to the direction of the gradients we applied to detect water motion. But what did we do here? We averaged them, and called this averaged value of the diffusion coefficients the ADC, the apparent diffusion coefficient. No need for me to rant again about why this isn't just called the average diffusion coefficient, but you would be right in doing so in my books. Mathematically, we calculated this ADC value for each voxel from the intensity on the DWI trace image, an image where we applied no diffusion gradients, what we call S0, as well as this term B representing the characteristics of the applied gradient field. All of this is covered in detail in the first lecture. So from these 2 images, the DWI trace and this calculated ADC map, we can spot a whole host of pathologies that we covered in the second lecture. But let's go back to this DWI trace image. Here is where we can do better. But first, if you enjoy these videos, consider liking and commenting, following us on social media, hit the join button to see ways you can support us further, and click that subscribe button below. Thinking about what we did to create this DWI image, it almost feels like we took a shortcut. You may even remember that sometimes this is called the isotropic image, meaning diffusion is equal in all directions. But is that accurate? Let's go back to these source images created with each diffusion gradient that were then averaged to create this DWI trace image. I've mixed up the order, and my question for you is, can you pick out which gradient we applied based on the appearance of the image alone? I've put a set of axes in the bottom left corner for orientation. Can you spot the image that was created with a gradient applied across the x-axis? Did you pick this one? How so? Well, since we expect to see signal loss in areas where protons are moving in the x direction due to this diffusion gradient we applied across the x-axis, let's look for areas of signal dropout along the x direction between the 3 images. Check out the genu and splenium of the corpus callosum. See how we have substantial signal dropout in these areas in the direction of the x-axis on the middle images. It's so pronounced on the top image, it almost looks like there's nothing there at all. Now that we know what to look for, which picture was created by applying our diffusion gradient across the y-axis? Is there a picture here which looks like it's losing signal along the y direction? That's right, the picture on the left. If we zoom in and compare this region, you can see there's a pretty striking band of signal loss here along the optic nerve tract. And finally, by process of elimination, you can guess that the image on the right is the one we generated after applying our diffusion gradient across the z-axis. Now this one is a little harder to discern, but if we zoom in on the deep brain structures, we see there is signal loss along the posterior limbs of the internal capsules on the right image and what resides in this region. The corticospinal tracts, which run from head to toe in the z direction on this coordinate system. And we can also see the reverse. If we look back at this structure here, the splenium of the corpus callosum, which mainly has fibers running in the x and y directions, you can see on the right image we have almost no signal loss because there is little water moving in the direction of our z gradient. A nice little check to make sure our theory holds true. So going back to our original question, are these images isotropic? Does our signal look the same in all directions, or is there very important information here about the direction of water movement in our pictures? Let's explore this a little further by looking at this image of the brain as if you were face to face with someone. Zooming in here a bit, you can see our coordinate system in the bottom left corner and how we're now looking at the x and z dimensions with our y dimension coming into and out of the screen. Let's just try to visualize what is going on with a drop of water here, within the CSF of the ventricles. What direction or directions do you think this drop of water can move in through any of our means of diffusion? Well, nothing is really restricting it. We're just sitting in a sea of other water molecules, so we can move down, we can move right and left, we can even move deeper into the ventricles or closer. So this drop of water flowing freely within the CSF does not appear to be restricted by any particular direction, and is in fact displaying isotropic diffusion. So what kind of signal should we see within this region on our diffusion-weighted images? Almost none, especially on these higher B-value diffusion images. The water is free to move randomly in all directions, and therefore we should see no significant signal change here in between the gradients. That is the key. The signal stays the same no matter which direction we apply the gradient. Now let's go back to our experiment, except this time, imagine a drop of water here, within the corpus callosum. Now this region is special because it contains bundles of neurons communicating between the two cerebral hemispheres illustrated here. Do you think our drop of water is free to move about in all directions like the previous example? Or could it be that it's bound along these highly organized white matter tracks and will move most freely along the direction these tracks run in? The x direction in this example. This is what we call anisotropic diffusion, movement of our water protons that is not equal in all directions, but in fact prefers to move in a particular direction due to the surrounding microstructure. We're not limited to this example. In fact, anywhere we have highly organized white matter tracts, such as the corticospinal tract shown here, we'll get this anisotropic diffusion, preferential movement of our water molecules along these tracks. Going back to our diffusion-weighted images, you can now understand what it is we're actually seeing. There's no change in signal between the different gradients in areas where water moves freely, within the ventricles, and significant changes in signal along our white matter tracts, particularly where the direction of the tract aligns with the direction of our gradient field. So in fact, we have both isotropic and anisotropic diffusion in these images. So when we create this DWI trace image, average all the signal from the individual images together, we lose this precious information about the direction water is diffusing in the image and how strong that diffusion is. But why do we even care? Let's go back to the picture of our corticospinal tract, a very important structure in the brain carrying signals for voluntary motor control throughout the body. What if there's a brain tumor right next to these tracts? and the surgeon wants to get as much of the tumor resected as possible without entering the tracts, because, as you can imagine, some pretty devastating things can happen if you start severing the cables that these very important signals are carried on. Is there a way we can figure out where these tracts are and the direction they're traveling via how our water molecules diffuse along these tracts? To do this, let's consider a cube of matter we think is located along this white matter tract. Let's apply the steps we know up to this point. We're going to run our diffusion-weighted sequence 3 times. Once while applying our diffusion gradient across the x-axis, once across the y-axis, and once across the z-axis. Let's illustrate this on our cube of matter. We run this sequence with our diffusion gradient along the x-axis, and this helps us detect diffusion along the x direction. We next run our sequence again, except with our diffusion gradient along the y-axis, and with this we will detect diffusion in the y direction. Finally, we repeat these steps with our diffusion gradient along the z-axis, and with this we detect diffusion in the z direction. So to summarize, we've run 3 sequences with diffusion gradients along the x, y, and z axes, and we have enough information to determine diffusion in these directions. How do we calculate this? Well, it turns out, we have pretty simple formulas for this that we covered in the first lecture. The signal of our image is equal to the signal of the baseline image without diffusion gradients applied, our so-called B0 image, times the exponential of the negative b value times our diffusion coefficient in that direction. If we do a little arithmetic and put this in a matrix form, we get this. Now, for those of you that aren't familiar with matrix math, the way you read this is to go along the rows. So diffusion in our x direction equals -1 over b times the natural log of the signal generated with our x gradient divided by our baseline signal. You can see we have 3 equations and all the information needed to solve for the value of these individual diffusion coefficients. So it's actually pretty easy to solve for these diffusion coefficients in our DWI trace formula. All the information is there, it's just a little math. But is this useful in our goal of accurately determining the location and direction of these white matter tracts next to this tumor? Let's say that after performing the sequences and doing the math, we calculate the diffusion coefficients to be this, with diffusion occurring greatest along the x-axis. Is this information enough to go to surgery with? So you can see there's a problem here. We're limited to only the directions we applied our diffusion gradients along, and while in this case the diffusion coefficient with the greatest value is along the x direction, it does not mean this is the true direction the white matter tract is running. This is the true direction, shown here in blue, and what we need to find in order to accurately model these tracts for surgery or other purposes. So we've come to a major problem. It's highly unlikely that our white matter tracts will perfectly align in the direction of these gradients along the x, y, or z axes. It's almost certainly going to be off diagonal, somewhere in between. It could be here, or even here. So this becomes a much harder problem to solve, as we'll see. But first, we need to figure out an accurate way to model what's going on here. Remember that diffusion is the movement of water protons over time, and this diffusion coefficient is dictated by fixed laws, which state the diffusion coefficient times this driving concentration gradient creates a flux of particles through an area over time. Let's demonstrate what we mean on our cube of matter here. If diffusion is the flux of particles through an area over time, we need to first pick an area. Let's look at this surface of the cube, the one which the x-axis goes in and out of. Here we see our water molecules, and let's pretend our white matter tract is perfectly aligned with our x-axis, so that over time our water molecules will diffuse in the x direction. In this scenario, the diffusion along our tract will be equal to dx, and we already showed this is easy to calculate, so we're done, right? Not so fast. What are the odds that diffusion just happens to be exactly along one of these main axes we chose? What is more likely is that our molecules will not move perfectly along the x-axis, but at some angle, shown here. Now things get interesting. In order to describe this vector representing water movement through this surface, we need to break it down into its individual components with respect to the surface. So this tract with a component along the x-axis and perpendicular to the surface we'll call dxx, meaning in the direction of x along the x surface. But then we'll need components parallel to the surface, which we will call dyx, the component in the y direction on the surface of x, and dzx, the component in the z direction on the surface of x. I warned you this was going to get a little crazy, but all we are doing is describing this three-dimensional diffusion vector with respect to this surface x. Remember, diffusion is the flux of particles through a surface. But wait, is this the only surface we have on this cube? We actually have 6 surfaces, but only 3 of them are unique, the others are just repeats. So we have to do this for the 2 other unique surfaces. Let's now say this is the direction of diffusion along our tract, through the y surface. To describe this in 3-dimensional space with respect to this surface, we'll again have a component perpendicular to the surface along the y-axis, dyy, again meaning along the y-axis of the surface y, as well as 2 components parallel to the surface y, dxy along the x direction of the surface y, and dzy along the z direction of the surface y. 2 down, 1 more to go. Finally, if our diffusion happens to be through our z surface, we'll have a component perpendicular to the surface and parallel to the z-axis, dzz, and 2 components parallel to the surface z, a dxz and a dyz. I know this is complicated, but we're so close to solving this. Stick with me a bit longer. Looking at all of these together, we have just derived all the possible variables we would need to calculate diffusion along any surface of this cube. And if we arrange these into a nice matrix, we get what we call a diffusion tensor matrix. Why the term tensor? What does this mean? Now, there are better and more in-depth lectures on this subject on YouTube, but it originally comes from studying the properties of how a cube of matter deforms when a tensile stress is applied to it. Tensor matrices are an extremely powerful mathematical tool that helped this guy develop his theory of general relativity. Let's point out a few key features of this tensor matrix. Notice that we actually have repeats in this matrix. dxy and dyx are essentially the same due to conjugate symmetry, as are dxz and dzx, as well as dyz and dzy. How does this help us? Well, our goal is to solve the values of this matrix, and because of these symmetric variables, it turns out we can ignore these bottom ones because there are really only 6 independent non-collinear variables in this matrix we need to solve for. This means that in order to determine the direction of diffusion in our cube of matter, we need at minimum 6 unique diffusion sensitization gradients. And as you can imagine, we're going to need to make sure the direction of these gradients are well arranged in space, particularly these off-diagonal elements, to make sure we're detecting the diffusion. What do I mean by off-diagonal elements? Well, notice that the diffusion coefficients along the diagonal of the matrix are actually special in that they are the ones perfectly aligned with our x, y, and z axes, and these have a special mathematical term: the trace elements of the matrix. Aha! This is why we call this image our DWI trace, because we only apply gradients along our x, y, and z axes to generate it. Therefore, it only contains the diffusion coefficients in the direction of our axes dxx, dyy, and dzz, simplified here. And as we said before, the best thing about these diagonal elements is that they're easy to solve for. It's simply these independent equations. But in order to perform diffusion tensor imaging so that we can more accurately characterize the direction and magnitude of diffusion, we need to expand this to include our off-diagonal elements dxy, dyz, and dzx. Now the right side of this equation expands in a similar form to what you would expect, except instead of saying sxx or sxy, we just give it a number, s1, 2, 3, and so on. This is still the signal of the image we generated after the sequence is run, so it's a known value, but you'll see here in a second why we label it this way. So while this seems like a natural evolution, the truth is the left side of the equation is not so simple. We are now describing not only the magnitude, but the direction associated with each. And as these are vectors that we need to describe in three-dimensional space, we need to introduce unit vectors as well as some geometry to the equation as shown. Yikes! Don't get lost in the math here. Just know that the first matrix on the left represents the direction of applied gradients. The second matrix is our diffusion tensor containing the diffusion coefficients we want to solve for. And the matrix on the right is simply derived from our output signal and B value of the applied gradients. The big picture is that now we've developed 6 independent formulas to solve for 6 independent variables. And we can solve for these values by applying 6 well-directed diffusion sensitization gradients and measuring the signal for each gradient. Visually, it looks like this. We apply our diffusion gradient across the x-axis and we detect diffusion occurring solely along the x direction. We then run the sequence again, this time with our gradient across the y-axis, detecting diffusion occurring solely along the y direction. We run it again, now with our gradient across the z-axis, detecting diffusion only along the z direction. And those are the easy ones. Now we have to interrogate these off-axis directions. Let's say we apply our gradient in this direction, now with a component in all 3 axes. In turn, we'll get varying values for all the diffusion coefficients since we've got a foot in every direction, so to speak. And we'll get a different set of values for a different off-axis direction. And so forth. But we know the direction and strength we applied these gradients and the signal we measured, and through these nifty formulas we can solve for these individual diffusion values. Knowing these, we can figure out both the direction and maximum value of diffusion, which we expect to be in the direction of our white matter tract. Now let me ask you, do you think this is enough? Through these 6 unique directional diffusion gradients we applied, how confident are you that we got one of these gradients along the exact direction of the tract to produce that maximum value? Or is it possible that we got an estimate, much better than we did before and in the general direction of the tract, but not close enough? Does it matter? You tell me. You've got a brain tumor and they're going to be resecting it as close as they can to these really important neurons that control your movement. Is a rough estimate good enough, or do you want to get as close as you possibly can to the true location and direction of these? I would want the latter. So while we need a minimum of 6 unique directional diffusion gradients and our B0 image to perform diffusion tensor imaging, in order to perform tractography and to give us the accuracy we need to use this clinically to perform things such as surgery, we're going to need more gradients, a lot more. Because the more unique directions we can apply our gradients, the more likely we'll approach that true direction of the tract and the more accurately we can characterize them. This means sometimes employing up to 64 unique directional gradients for one exam, shown here. This isn't a hard number, we can certainly do more, but this will come at the expense of longer imaging time, and there will be some optimal combination of number of gradients applied and their spatial distribution that will provide us with quality tractography for our clinical needs. So how does this play out mathematically? If we go back to our equations, we have 6 independent equations with 6 independent variables in our diffusion tensor matrix. We're not adding more variables, we're simply performing more runs of the sequence with our off-axis diffusion gradients. So on the left, we're going to write this in a more generalized form. Starting with the direction of the first gradient all the way to the n number of gradients applied. We'll do the same on the right. Starting with the signal S1 generated from the first run of the sequence all the way up to n number of sequences. And if we perform 64 gradients like we showed in our previous example, the formulas would look like this. What this is going to do is give us some redundancy with our equations. We're generating way more equations than the number of variables in our diffusion tensor matrix. This will maximize the chance we'll place one of these diffusion gradients as close as possible to the true orientation of our white matter tract. And using linear regression models, we can solve for these diffusion coefficients, allowing us to calculate the direction of our tract that is as close as possible to the true orientation of the tract. Wow, that was a lot of work to get to this point, but how amazing is it that we can do this? Let's wrap this lecture up by talking about a few of the things that we can do with this hard-fought information we just obtained. So we have calculated these diffusion tensor values for not just one cube of matter, represented by the voxel of our image, but for every single voxel of the image. And we're going to need some sort of algorithm examining how the diffusion in each voxel relates to the voxels adjacent to it. That's beyond the scope of this lecture, but just know there are algorithms with names such as fact that do this. The reason it's important is that we need to weed through all this mathematical noise to figure out, hey, the voxels in this region seem to have a similar direction of diffusion suspicious for an underlying white matter tract. If we can identify those voxels, we can use the information to generate these pretty images of suspected white matter tracts we refer to as diffusion tractography. Now, while these look impressive, you have to use specialized software to manually select the white matter tracts you're looking for, since there are many tracts that cross within the brain, and this introduces an element of error. What can be more useful to surgeons and radiologists is something called fractional anisotropy. If we take these voxels and look at the diffusion coefficients, we can determine the maximum value of diffusion and its direction, which we expect to occur along the tract. We'll call this Dmax, or lambda1, our primary eigenvector and eigenvalue. You can do a whole deep dive on this confusing terminology, so if you don't know what that is, don't worry, but I want to at least give you the right words and symbols if you want to dig further into the math. So if we have this primary vector, which is along the direction of maximum diffusion, we might also want to know how much diffusion is occurring orthogonal to this direction, which we'll call our radial diffusion, our second and third eigenvectors and eigenvalues. Why would we want to do this? Because it gives us an idea of how isotropic or anisotropic diffusion is within this voxel. Think about it. If the diffusion is almost entirely anisotropic, meaning moving in a single direction, our primary diffusion vector is going to look like this, and our secondary and third radial diffusion vectors will look like this. Practically zero. If we drew this out, this would look highly elliptical. So if an extremely anisotropic diffusion looks like this, what do you think isotropic diffusion will look like? It'll look like this. Diffusion in this case is occurring equally in every direction, what we call isotropic diffusion. And if you drew this out, it would look like a sphere. And of course, we have everything in between. By identifying these major and minor axes of diffusion, we can do some math. This is the last math of the lecture, I promise, but if we use this formula consisting of our primary and secondary and tertiary eigenvectors and eigenvalues, we produce a value between 0 and 1, 0 being isotropic diffusion, equal in all directions, and 1 being anisotropic diffusion, diffusion only along one direction. We can then use these values of 0 to 1 for each voxel to produce these beautiful images where the closer to 0 the voxel is, the darker it is, and the closer to 1, the brighter. Notice how these bright areas look an awful lot like white matter tracts where we expect to find highly directional anisotropic diffusion. But wait, we're not done. We have information not only on the magnitude of diffusion, but also the direction. And we can color code direction onto this image to make our colorized fractional anisotropy maps. We can choose whatever colors we want for this, but a common method is to code diffusion occurring predominantly in the left to right direction as red, anterior to posterior direction as green, and cranial-caudal direction or head to feet as blue. These colorized fractional anisotropy images can be of great value to surgeons and radiologists, as these really let you see where the white matter tracts are running in relation to that tumor or other area of the brain that needs to be resected. This has been one technical lecture, and it may require multiple passes to fully absorb, but I hope it at least gives you an idea of what diffusion tensor imaging is and how we use the information to generate useful images for our radiologists and surgeons that can really help people. On the next episode of MRI Physics Explained, it's the time you've all been waiting for. We are going to step away from this series on MRI pulse sequences and finally start tackling subjects such as K-space, starting off with a lecture questioning the very reality of current MRI physics education. We'll see you next time. As always, this is Dr. TE signing off.